Addendum to slides 24 and 23. So we've said in this slide, let's compare AZ equal R theta double dot with minus R omega to the square theta. And it was said that we wanted to verify if the differential equation theta double dot plus omega square theta equals 0 coming from the Newton law. In this system, this is not strictly speaking correct, as we should have taken into account minus theta dot over tau, which take into account the fact that we have dissipation in this system. Indeed, if we start from the Newton law, then we come immediately, if we take into account dissipation with lambda V, where lambda is dissipation coefficient viscous flow, which is obvious here because it's probably the wire that's doing the job and not at all the ambient air. But let's say that we can describe it due to the fact that we have seen that exponential minus t over tau is doing the job. Then along the n vector, the differential equation comes to the classical one with correction, that's minus lambda r theta double dot, theta dot. And when we say that theta is small, then we come to this classical differential equation, theta double dot plus omega square theta, but equal here minus theta dots over tau. So the question is, do we have that to take that into account? So here we believe not, because we're working with a system that has a slow dissipation that's oscillating very fast. That is described by the fact that we have a quality factor of about 100. But let's see if this is correct experimentally, and in the following here we plot both the experimental value, these are in red. In black we have the differential equation taking into account dissipation, and in blue the differential equation without dissipation taken into account. And what we observed essentially is that at the scale we're looking at, which is sufficient for our purpose here, we could push further, but here let's say that we stop at this level of rigor. And then what we observed is that the curves are only distinguished. It's not even easy to see if you have free curve here. So that's the reason why in our simple approach then we stopped using for this verification the dissipation. And what we show here indeed is that with that level of analysis, then we cannot prove at the end directly in the equation that we have this dissipation term. We see it from the relaxation behavior along the time, but not for each period.